Exercise 1. A skier considered as a particle mass slides down a smooth snowy slope at an angle of 25 degrees. The skier's mass, including the equipment, is 75 kilograms. Let us be the name of the system skier equipment. Name and represent the external forces acting on us. So this question is divided into two parts. Naming and representation. Half the grade is for the naming, for listing the forces, and half the grade is for the representation. So weight, you have to write W vector, normal reaction of support, and vector. And concerning the representation, as you can see, the normal reaction of support is perpendicular to the inclined plane, and the weight is represented vertically downward, and you have to it's not enough to draw a segment. If you only draw a segment, this won't be considered correct because you have to show the direction of the force. So it should end with an arrow here, and it's necessary that you write the name of the force. So here you have N vector, and here you have W vector, and showing the arrow is downward. Now concerning the second part, determine by applying Newton's second law of translation and motion, the acceleration of s, then deduce the nature of motion. So you are given that you have to start with Newton's second law. Now you have to say summation, this is the statement of the law, summation of f external vector, summation of f external vector, it's necessary that you write the vector here, equal ma vector. So we have here a vector quantity equal a vector quantity. First you start with the first statement, which is summing up all the forces acting on the object. So we have n vector plus w vector equal ma vector. Now when we do projection along x-axis for the inclined plane, we consider here the x-axis to be parallel to the inclined plane, and the positive as long as the man is sliding or the skier is sliding down. So we consider the positive direction of the x-axis in the sense of motion. So when we project, we no more use vector notation. We have only, as you can see, wx. So I projected, this is w. I did projection on x-axis. Then the point joining the origin of the orthonormal system to the orthogonal projection represents wx. Here I want to note that in the given, you are given that the skier is considered to be a point mass. So I then represented it as a point, and I took this point mass as the origin of the orthonormal system. So then I represented all the forces starting from this point. You have here the normal reaction of support is upward and the weight vertically downward. Alright, so we do projection of the weight on the x-axis as I said before. This is wx. When we do projection, no more vector, we don't use anymore the vector notation. It is first wx equal ma, not w. If you write w alone, this is wrong. This means that you're considering the weight, the whole force, including its x and y, the magnitude of the whole force. And this is wrong. We only consider the x component of the weight. So wx, which is equal w sine alpha. Alpha is 25 degree here. So aside, as you can see, doing some geometric analysis, if the angle, the inclined angle, or the angle of the inclined plane is 25 degrees, so this is not, if you consider this triangle here, this is 90, this is not the 25, this is the complementary, and these are here, these are parallel to each other. So this one is not the 25, and this one is not 25. Okay, so in the bigger triangle, including the weight as a hypotenuse and the x component of the weight as one of the legs, we have then this, if this is not the 25 degree, this is the complement of the 25 degree, and this is 90 degrees, so this one is the 25 here. Okay, and the side facing the 25 degree is the x component. That's why we say sine 25 is wx over, and the hypotenuse, which is the side facing the right triangle, is the weight. Cosine 25 is wy over w. If you do cross multiplication, wx is w sine 25. As you can see, we have to write it in details. Then you substitute w for mg, sine alpha equal ma. Here it happens that you have only like one product on one side and one product on the other side. So you can simplify for m, divide by m both sides. So you are left with g sine alpha equal a, then the acceleration is 10 sine 25, and a will be equal 4.2 meter per second squared. So if you don't write the unit, you will lose grades. If you write meter per second, you lose grades because meter per second is the unit of speed, not acceleration. If you only if you only write 4 without writing any decimal point, taking any decimal digit into consideration, you lose grades because you have to take 1 or 2 digits at least. Okay, this affects the results. The motion is UARM. I've been repeating this for many times. You have to justify it. You have to justify why it's uniform, why accelerated, and why rectilinear. So accelerated since A is positive, uniform since it's constant independent of time, and rectilinear since the trajectory is a straight line. This is concerning exercise 1, and we have now in part 3.1, knowing that he starts sliding from the top of the inclined plane at 3 meters per second. Calculate the speed of the skier as he reaches the bottom of the slope after 10 seconds. So as long as we prove that it is UARM, so now you have to apply the general rule of VV equal AT plus V0, 4.2 times 10 plus 3. So here if you consider only 4, it will be 4 times 10, 40, plus 3 is 43 meters per second. You will get that he reaches the bottom with a speed of 43 meters per second. However, if you take a decimal digit, like here 4.2 times 10, this will be 42 plus 3, so the final speed is 45 meters per second. See how the results differ upon considering more digits, so you have to be more accurate. And concerning the distance covered, d equal half at squared plus b naught t, many students forgot to substitute this term. So we have half 4.2 plus into 10 squared plus 3 into 10. We are given the values in the SI unit, so we don't need to convert anything. So 210 plus 30 is 240 meters. Now concerning the height, you are given that he started from the top and he covered, now we calculate that he covered a distance of 240 meters, and you are asked to find the height of the inclined plane. So starting from this point, you can see that this is a right triangle here. Okay, this is a right triangle. So simply looking for height, which is the side facing the 25 degree, and given the distance, which is the hypotenuse of this right triangle, we apply sine 25 equal height over distance, opposite over hypotenuse. So height is equal d sine 25 equal to 140 sine 25, 101.42 meters. This is concerning exercise 1. Now concerning exercise 2, you have a bar magnet is held close to a steel ball of mass m equal to kilograms hanged to a rope. The ball deviates until it reaches an equilibrium position as shown in the adjacent figure. So you can see that the rope is making a 30-degree angle with the vertical, and the ball is at a certain distance away from the magnet but being attracted by it and is at equilibrium. Now name and represent the forces acting on the ball. Okay, again same thing here, you have to name and represent. Weight W vector, magnetic force M vector, tension T vector. Tension is along the rope, magnetic force should be represented on the ball, not on the magnet, because we are considering the forces acting on the ball. Some students represented the magnetic force that is exerted by the ball on the magnet. No, this is not the question. Okay, so you have to consider the force exerted by the magnet on the ball, and the magnet is pulling the ball to the left. So you start to represent, because it's acting at a distance, you start representing it from the center of the gravity of the ball. And you have also the weight is acting vertically downward. Command is represented starting from the center of the gravity because it's a force acting at a distance. Then you are asked to show that the magnitude of the force exerted by the rope on the ball is approximately 23 newtons. So indirectly they're asking you to calculate the magnitude of the tension force, as long as you're given that it is at equilibrium. So F external forces, F vector equals 0 vector. This is the equilibrium condition. We sum up all the forces, T vector plus W vector plus M vector. Here I want to note something. If you add any force, and for example some students added normal reaction of support, so you will lose grades for this. Okay, so because considering more forces that are not really acting on the object, it's just like missing the forces acting on it. So T vector plus W vector plus M vector equals 0 vector. Now projection along here, why did we start with projection along y-axis, not along x-axis? So it's not a rule that we have always to start with projection along x-axis, okay? The point is that if we just look at the problem before we start solving, try to solve it like mentally. Tension is you have the magnetic force to be a horizontal force, and the weight is a vertical one. And tension is the only oblique one, so you expect that you will have to project T on the x-axis and on the y-axis to obtain its x component and y component respectively. So if you're going to work along x-axis, you're not given the magnitude of the magnetic force, and you know nothing about the tension, so you also don't know the x component of T. So you cannot start here with two unknowns projecting along x-axis. However, if you project along y-axis, you will have Ty and W. Okay, W, you know that it's mg, and m is given and g is given. So you will only be dealing with one unknown, which is T. That's why we start by projecting along y-axis. Do not write here project along x-axis and do projection along y-axis. Okay, you write projection along y-axis and do project along y-axis. Alright, and you have to show this on the figure as I'm showing here. So this is the y-axis, positive, and this is the x-axis, and this is the positive sense. Okay, so what do we have on the y-axis? I then considered the ball to be a point object, which is the origin of the system, autonomous system, and I represented the magnetic force horizontally, weight vertically, downward, tension oblique, and then I projected T on the y-axis and T on the x-axis, as you can see, Ty, Tx. So now when you project, you no more use vector notation. You have plus Ty is upwards in the positive sense, minus W in the negative sense equals 0. So Ty equals W. And here aside, you can see that this is the angle 30 degree. The side facing it is Tx. So sine 30 is opposite over hypotenuse, which is T. And so sine 30 is Tx over T. And cosine 30 is Ty over T. So now Ty is T cosine 30 mg, then T, which we are looking for, is mg over cosine 30. It's 23.01 Newton, which is approximately equal to 23 Newton. Then you are asked to find the magnetic force, again using the equilibrium condition. Now projecting along x-axis, you have Tx in the positive sense, as you can see, and m in the negative sense. So that's why we write Tx minus m equals 0, so Tx equal m. Tx is T sine 30, we found the relation already here. Tx is T sine 30. Now we have T, we have sine 30, so m is 11.5 Newton. And finally, you are asked to state Newton's third law. When you are asked to state a law, you have to use words. Do not only use symbols and mathematical relations. So Newton's third law, if a body A exerts a force, you have to name this force F vector A on B on a body B. Then at the same time, B exerts a force F vector B on A, such that F vector B on A is minus F vector, this is A on B. Okay, this is A on B. And such that the magnitude now are equal. So you don't put minus for magnitude, you put minus for vectors to show that they act in opposite directions. So FB on A is equal FA on B. Therefore, M, magnetic force that we defined above, is the force acting exerted by the magnet on the ball, which is equal in magnitude to the force exerted by the ball on the magnet, equal 11.5 Newton.